If you've ever needed to give a remote employee, a contractor, or even an automated workflow access to something sitting on a private network, something like a database, an internal web application, a machine on a factory floor, you already know how uncomfortable that conversation gets. The traditional answer has almost always been a VPN. You punch an inbound hole in the firewall, you hand out credentials, and you tell yourself it's fine. It usually isn't. VPNs put users on your network. They don't put users on the specific application they need. That gap between on the network and allowed to access this one thing is where breaches happen. There's a better model. It's called Zero Trust Network Access. And today we're going to walk through exactly how Kasm Workspaces implements it using OpenZiti. Before we go any further, a quick note on deployment options. Everything in this guide works with self-hosted OpenZiti, which is fully open source and free to run. It also works with NetFoundry, the company behind OpenZiti, which offers a cloud platform built on the same technology. If you'd rather not operate the infrastructure yourself, NetFoundry's hosted SaaS is a supported path. We'll point to that option as we go. Here's what we'll cover in this video. First, we'll talk through the problem, why network layer access control isn't good enough, and what zero trust actually means in practice. Second, we'll walk through the OpenZiti architecture, its controllers, routers, identities, and explain why private resources can stay completely unreachable from the internet. Third, we'll explain how Kasm integrates with OpenZiti, what happens automatically, what you configure, and how an identity gets from Kasm's user database into a live workspace session. And finally, we'll do a real configuration walkthrough. We'll publish a private service, wire it into Kasm, and walk through two practical scenarios for delegating access. One scoped to an individual user, one scoped to an entire workspace image. Let's get into it. The fundamental problem with a VPN is the thing that also makes it feel simple. It gives you the network. When a user connects through a VPN, they appear on your internal network with an IP address. From there, policy is mostly just routing. If a firewall rule allows traffic from the VPN subnet to reach a server, any user who's connected through the VPN can reach it too. You get coarse network level access, not precise application level access. This creates two problems that compound on each other. The first is blast radius. If an attacker compromises a VPN credential through phishing, credential stuffing, or a misconfigured endpoint, they're on the network. They can move laterally, they can scan. A single compromised account could be the beginning of a much larger incident. The second is operational friction. Every new resource that needs to be accessible over VPN requires firewall rules. Every remote site, every vendor, every temporary contractor, the rules accumulate. The documentation falls behind, and eventually someone opens a rule they never intended to open permanently. Zero Trust inverts this model. Instead of granting network access and trusting users to stay in their lane, Zero Trust requires that every access request is verified against an identity and a policy for every connection, every time. The network is no longer the trust boundary, the identity is. In practice, this means that resources are never directly reachable from the internet. There are no inbound ports to scan or attack. Users don't get on the network. They get access to specific named services and only the ones that policy allows. Every connection is authenticated with a cryptographic identity, not a static password, and access can be revoked instantly for any individual identity without touching the network topology. This is exactly the model that OpenZiti implements, and it's why it maps naturally onto environments that historically relied on strict network segmentations, things like industrial systems, OT environments, multi-tenant infrastructure. If you can't have users directly touching a network segment, but you still need them to reach specific surfaces on it, identity-based access gives you that precision without requiring a change to the underlying network. OpenZiti is an open source ZTNA fabric. It consists of a small number of components that work together to create an encrypted overlay network where services are reachable by name and identity, not by IP and port. Let's walk through some of the key pieces. The controller is the control plane. It holds all of the identities, services, and policies. Every enrollment, every access decision, every route lookup traces back to the controller. Nothing moves in the fabric without the controller's authorization. The controller doesn't carry any data plane traffic itself. It's a policy enforcement point, not a traffic bottleneck. That means you can run it in a highly available configuration with multiple nodes using graph consensus and lose any single node without disrupting live sessions. We'll touch on that more when we talk about high availability. Edge routers are the data plane. There are two flavors, public routers and private routers, and they have very different jobs. Public routers sit at the edge of your infrastructure, in a cloud region, in a DMZ, or both. They accept inbound connections from clients. Kasm sessions connect to a public router to get into the fabric. External users running the OpenZiti Edge tunnel on their own device also connect through the public routers. These routers carry traffic, but they don't host services. Private routers are different. Each private router lives next to the resources it exposes, on the same network as the database, the internal web service, the machine you're protecting. And here's the key architectural detail. Private routers make only outbound connections. They connect to the controller and to the public routers. They never accept inbound connections themselves. What that means in practice is you don't need to open any inbound port at the resource site. You don't need to modify the firewall. You don't need to expose anything. You deploy the private router, it phones home to the controller, and suddenly the services it wraps are available to authorized identities without ever being reachable from outside. For environments where network modification is expensive or politically difficult, things like industrial segments, co-located data centers, partner facilities, this is a significant operational simplification. Identities themselves are certificate-backed objects. Every user, every workspace, every router has an identity. Identities are enrolled with the controller and carry cryptographic credentials. They are the subject of every access policy. Services are logical targets. A service represents a specific destination, a host, and a port behind a private router, and is given a name. Clients in the fabric reach services by that name. There is no IP address to guess, no port to scan. The service only exists as an addressable thing for identities that have been explicitly granted access to it. This is what we mean by a dark network. From the outside, the resources that you protect are simply invisible. Before we jump to a practical example, we have one last thing to cover. Kasm's integration with OpenZiti is built around an egress provider model. An OpenZiti egress provider in Kasm is a connection to an OpenZiti controller, self-hosted or hosted by NetFoundry, that Kasm uses to automatically manage identities on your users' behalf. We should be precise about what Kasm does and what OpenZiti does. Kasm decides who gets a managed identity. You configure an egress provider and you map it to specific users, groups, or workspace images. Kasm's reconciler watches those mappings and creates or removes OpenZiti identities in the controller as they change. OpenZiti decides what each identity can reach. Having a Kasm managed identity in the controller is the starting point. That identity can't reach any service until an OpenZiti policy grants it access. Kasm never overrides that. The policy layer stays fully in OpenZiti's domain. The identity lifecycle looks like this. When you map a provider to a user or workspace, Kasm creates an identity in the controller with a predictable name, something like Kasm user Alice or Kasm workspace Chrome. It enrolls that identity automatically and stores the resulting identity JSON. When a session launches, Kasm's egress sidecar retrieves the stored identity, writes it to a secure namespace, and starts a ZT tunnel process inside the container. DNS inside the session is configured to resolve ZT service names. The user or application running inside the session can now reach services by their ZT name, something like gitlab.corpay.zt or db.prod.zt, as if those services were right there on the local network. When the session ends, the tunnel stops. When a user is removed from an egress mapping, the identity is removed from the controller at the next reconcile cycle. This means that there are no stale credentials sitting around at tunnel time or at access granting time. This is how the lifecycle works. Now let's see it in action. To make deploying and operating an OpenZiti environment for Kasm as straightforward as possible, we built a CLI tool called KZD. It wraps the OpenZiti API behind an opinionated deployment model. Public routers handle transit, private routers host services, and access is managed through a consistent tagging scheme. KZD handles the things that might otherwise be repetitive or error-prone, bootstrapping the controller and routers, managing role attributes that join identities to policies, and giving you simple commands for publishing services and granting access. If you're running self-hosted, KZD is your management layer. If you're using NetFoundry's hosted platform, then the OpenZiti primitives, identities, services, and policies are managed through NetFoundry's console, and Kasm connects to NetFoundry's controller the same way it would connect to a self-hosted one. Either path produces an admin identity JSON that you paste into Kasm once, and from there the lifecycle is identical. For large or complex deployments, NetFoundry's managed SaaS removes the operational overhead of running controllers and routers yourself. Let's look at how quickly we can go from nothing to a working zero trust network. If you'd like to follow along with this section, you can follow our OpenZiti Quick Start Guide available in our documentation. We have a Linux VM with a public IP and a DNS record. We'll stand up an OpenZiti environment from scratch, publish a private Nginx as a service, wire it into Kasm, and prove we can reach it from a workspace session. To begin, we'll install KZD. Once installed, you can validate that it's inside your path by running KZD version. The first step to setting up a network in OpenZiti is deploying the controller and public router. The single command we're about to run bootstraps an OpenZiti controller, a public router, and an admin identity, all in Docker Compose, all on this host. If you'd like to figure out the values for your deployment, please reference the documentation available in the Quick Start Guide. This generally takes a couple of minutes, and when it completes, you'll have the initial running core pieces of an OpenZiti fabric. Now that we've provisioned the core components, we're going to create a private network and provision a private router onto that network so that it can host services. In KZD's model, a network is a unit of grouping for related services. Think of it as a named scope. All of the internal services for a specific team, environment, or facility that are available from the same network location. To do this, we're going to run KZD network create and create a network called the demo. Now that we have that demo network, we're going to provision a private router onto it. A private router is the connector that will actually host the services inside that network. To provision it, we first generate an enrollment token. The router that we're about to deploy with the next command runs on the network segment next to the resources it protects, making only outbound connections with no inbound rules needed. This KZD deploy install command takes the generated token from the previous step. Now that both of those commands have been run, we can check the status of our routers. And we see our public and private router available. Next, we're going to start a private service and then publish it so that Ziti's aware. Normally, inside of your networks, you would have something you're trying to protect. This could be a GitLab, a database, a PLC, or any number of network accessible resources. For the purpose of this demo, we'll use Nginx as a stand-in for any private internal resource. The container runs attached to the private router's Docker network so that the router can reach it by container name. Now that we have a private service to target, we will publish it as a Ziti service. The alias flag sets the name that Kasm sessions will use to reach it. No real DNS entry required. We will do this through KZD service create. Next, we'll generate the Kasm admin identity. Kasm needs an admin level identity so it can talk to the controller and manage identities on your behalf. We create and auto enroll one. This is done through the KZD identity create command. This command writes Kasm API.json based on our input. This file is the one credential that you'll give to Kasm. You should guard it like any admin credential. For purposes here, I will open it up so that we can take it into Kasm. I will copy this. Now that we have this admin credential, we'll switch to a running Kasm instance. I'm logged in as an admin to a 119 or greater Kasm environment, and I'm going to go set up our Egress provider. So that is located under Infrastructure, Egress Providers. I'll go ahead and give this a meaningful name, Demo ZT, and it's an OpenZiti provider type. Next, I configure it with the admin token that we generated in the previous step, and go ahead and save this. At this point, Kasm is able to talk to the OpenZiti controller. We now will assign this egress to a Kasm workspace so that it can be chosen at launch time and it can generate the appropriate identities within inside of OpenZiti. So we'll go to the workspaces section. I have pre-installed an Ubuntu Noble workspace. If you do not see any here, you can install one from the available registry. We will go to edit this and we will go to egress and add our egress provider that we just configured. At this point, Kasm, in its next Guardian loop, will see that we have added egress to this workspace, generate an identity for it in Ziti, and generate identities for any users that have access to this workspace. We're now looking at the Ziti admin console that we just deployed. With the provider configured and mapped, Kasm has created OpenZiti identities for the users and workspaces in scope. But remember, having an identity doesn't mean having access. That's decided by OpenZiti policy. Let's walk through a few practical scenarios about how you can actually delegate access. We're going to start with scoping access to the most specific level. One user, one service. Maybe your user is a contractor who needs temporary access to your internal project tracker. You just don't want her to be able to reach anything else inside the network, just that one service. What we'll do is transition back to KZD and first list out the available identities of type user within the system. Here we see our two users that exist inside of Kasm that have been synced into Ziti. You'll see that they follow a consistent naming pattern, and this pattern allows multiple Kasm instances to be pointed at the same OpenZiti controller without any collision difficulties. What we'll do is list out the available services and see our available private Nginx that we deployed earlier. We will now grant a user access to that service. At any point, you can check who has access to a service and what a particular identity has access to. To check what an identity has access to, we use KZD access list. And we can see our newly added service here that this identity has access to since we granted access. And we can do the inverse query through KZD access who to determine which identities have access to this service. The next time this user launches a workspace, the ZT tunnel will have exactly that service in its allowed policy and nothing else. When you're done with the engagement, you can remove the grant through KZD access remove or remove the user from Kasm entirely to revoke the complete identity. Either way, access is revoked in the fabric layer immediately. Additionally, you can grant access through KZD identities for networks. So you can do something like KZD access grant, specify an identity and a network, or you can do a subscope through service sets, where you can assemble a set of services and grant access to all of them and revoke all of them at once. Both of those are slightly beyond this initial demo, but they're useful to keep in mind when dealing with access control. Now that we've granted access to this user, we're going to go ahead and launch a Kasm session and validate that we can correctly get to our network as expected. So I'm going to go to my workspaces, select the workspace I've added the egress to, and go ahead and launch with the egress provider enabled. Similar to gateway-based egress, you'll receive notifications if your tunnel is disconnected and reconnected, as well as initial connection. This is a configurable setting within general Kasm. What we'll do is open up Google Chrome, and we will make our way to our private service that we've deployed. This Nginx is not exposed to public internet. It lives on the private network, and we have reached it through the ZTNA fabric. What we'll do now is switch back to KZD, and we will revoke the access to this identity. Our user no longer has access to this particular service. And if we enter our Kasm session again, the same running one, and we go ahead and make sure our cache is not enabled, and we reload this page, it can no longer be reached. So access control and settings immediately apply to running and any other workspaces that will be launched in the future. This Nginx served from a container that had no public IP address behind no open inbound port through an encrypted zero trust fabric was accessed. The only thing that made this connection possible was a policy on an identity we changed to 0 underlying network traffic rules. For deployments where uptime is non-negotiable and in environments like industrial operations or critical infrastructure, understanding the high availability story matters. The OpenZiti controller supports a Raft consensus cluster. You run multiple controller nodes, they elect a leader and replicate state. If a leader goes down, the cluster elects a new one. Live sessions aren't disrupted because the data plane runs through the routers, not through the controllers. The controller only needs to be available for new enrollments, new access grants, and policy changes. Public routers scale horizontally. Add more routers and more regions, and the fabric load balances across them. Clients reconnect automatically if a router goes offline. Private routers make only outbound connections, so they don't create inbound exposure even in high availability configurations. You can run multiple private routers on a network for redundancy and service failover between them. KZD includes tooling for adding additional HA controller nodes to an existing cluster without taking the deployment offline. See the HA operations guide in our online documentation. Let's take a step back and talk about where this architecture provides the most value. The most common pattern is distributed teams needing access to private internal services, code repositories, build systems, internal tools, without putting those services on the internet or giving the whole team access to a production network. You publish exactly what's needed, grant exactly who needs it, and everything else stays dark. A second pattern is third-party and vendor access. Contractors, vendors, and integration partners need temporary access to specific systems. With this model, you create an identity, grant scoped access, and revoke it at the end of engagement. There are no VPN credentials to rotate, no firewall rules left open. A third area is environments with strict segmentation requirements, including OT and industrial systems. If your organization needs to reach resources across network zones that traditionally couldn't communicate directly, the private router model is a natural fit. The router sits on the isolated network segment and makes outbound only connections. The zone's network posture doesn't change, but authorized identities in the fabric can now reach specific services inside it. Kasm's session isolation and audit logging layer on top of that helps with compliance requirements like NERC, ISA/IEC, and NIST frameworks. Bringing this all together, OpenZiti gives you a zero trust fabric where private resources stay dark, access is decided by identity and policy rather than network topology, and every connection is cryptographically authenticated. Kasm integrates with that fabric by managing the full identity lifecycle for your users and workspaces automatically. You configure who gets an identity, OpenZiti enforces what they can reach. At session launch, the tunnel comes up. At session end, it goes down. There are no persistent credentials in users' hands. KZD makes the self-hosted path operationally straightforward. If you prefer a fully managed control plane with enterprise support, NetFoundry's hosted SaaS provides the same OpenZiti primitives through a managed platform, and the Kasm integration works identically in either case. The companion documentation, including the Quick Start Guide, the KZD CLI reference, and the HA Operations Guide, are available online. If you have questions or want to share feedback on the integration, please reach out through the community channels. Thanks for watching.